Have you ever wondered if there are boundaries to mathematical logic? If there are truths that, no matter how advanced our methods, remain forever unreachable? This is the enigma of logical limits, a concept that challenges our understanding of mathematics and logic itself. Back in the early 20th century, a logician and mathematician named Gödel wrestled with these very questions. He pondered whether the entire edifice of mathematics could be built on logical foundations, whether every mathematical truth could be reached through logical deduction, and whether a logical system could be both complete and consistent. His journey led him to a remarkable discovery that shook the very foundations of mathematical logic. This revolutionary finding is known as Gödel's Incompleteness Theorem. It's a theory that has two main parts, the first and second incompleteness theorems. Together, they reveal the inherent limits of formal logical systems, limits that challenge our deepest assumptions about mathematics and logic. The first incompleteness theorem tells us that in any logical system powerful enough to express arithmetic, there will always be true propositions that cannot be proven within that system. Imagine that, mathematical truths that are forever beyond the reach of proof. The second incompleteness theorem goes even further. It says that if a logical system is consistent, then it cannot prove its own incompleteness. So even if a system contains unprovable truths, it can't establish the full extent of these truths. These ideas were revolutionary. They challenged the formalist approach to mathematics, which sought to ground all of mathematics in logical and axiomatic foundations. They made us question our assumptions about the completeness and consistency of logical systems, and they've had profound implications for the philosophy of mathematics and our understanding of the limits of human knowledge. Gödel, a brilliant logician and mathematician, dared to ask these questions, and his answers were nothing short of astonishing. So join us as we delve deeper into the enigma of logical limits and explore the enduring legacy of Gödel's incompleteness theorem. Imagine a system, powerful enough to express arithmetic, yet incapable of proving all truths within itself. Welcome to the world of Gödel's first incompleteness theorem. This theorem, a cornerstone of mathematical logic, brings into sharp focus the inherent limitations of any formal system. Let's take a closer look. Gödel's first incompleteness theorem states that in any sufficiently powerful mathematical system, there are propositions that cannot be proven or disproven within that system. This is a bold assertion, going against the grain of centuries-old mathematical thought that believed in the possibility of proving every truth within the system's own framework. To put it another way, no system can demonstrate its own consistency. That's like saying you can't use the rules of chess to prove that a game of chess will always end. It's a paradox that strikes at the very heart of our understanding of logic and reason. But it's not just about the unprovable truths. The theorem also implies that there are truths that exist outside the scope of a system's internal logic. It's as if you're in a room filled with all the knowledge of the universe. But there are facts that exist outside the room, beyond your grasp, because the room itself doesn't acknowledge their existence. This is a profound concept. It's like saying there are books in a library that you can't read because they're written in a language the library doesn't recognize. The books are there, they contain truths, but you, limited by the confines of the library, are unable to access them. This theorem, therefore, challenges the very idea of a complete and consistent mathematical system. It's a subtle reminder that even within the seemingly rigid confines of logic and mathematics, there are truths that elude our grasp, that exist outside our neatly defined systems. In other words, mathematical truth is not confined by the system's internal logic, a profoundly unsettling idea. This is the paradox of consistency, a concept that continues to both baffle and fascinate us in our quest to understand the universe. But Gödel didn't stop there. His second theorem expands the scope of incompleteness even further. With this theorem, Gödel delves deeper into the enigma of mathematical logic, uncovering a startling truth about the nature of formal systems. The second incompleteness theorem is a continuation of its predecessor. It's like a riddle wrapped within a conundrum. Imagine that you're playing a game and you're given a rulebook. The rules are consistent, they make sense, and you can play the game. But then, you realize something peculiar. The rulebook, while containing instructions for the game, does not contain any rules about its own validity. This is the essence of the second incompleteness theorem. It states that if a logical system is consistent, it cannot prove its own incompleteness. In other words, even if there are true statements within the system that cannot be proven, The system itself lacks the capacity to establish the totality of these truths. The system, in a sense, is oblivious to its own shortcomings. This might sound counterintuitive. After all, if a system is consistent and logical, shouldn't it be able to recognize its own limitations? But this is the paradox that Gödel unearthed. A logical system, no matter how comprehensive or well-structured, is fundamentally blind to its own incompleteness. So what does this imply for the realm of mathematics? Well, it means that there are truths that exist within the system that can never be proven by the system itself. These truths are like invisible specters, present but forever out of reach. They are part of the mathematical landscape, yet they remain shrouded in mystery, beyond the grasp of formal logical demonstration. This insight into the nature of mathematical logic is both profound and unsettling. It challenges our understanding of mathematical truth and raises questions about the nature of knowledge itself. Can we ever truly understand the full extent of mathematical truth? Or are we forever confined by the limitations of our logical systems? The system, it seems, is forever blind to its own limitations. This is the conundrum of incompleteness that Gödel's second incompleteness theorem presents to us. It's a humbling reminder of the inherent limitations of logical systems and the enigmatic nature of mathematical truth. The implications of Gödel's theorem extend far beyond mathematics, shaking the very philosophy of logic. As we dive deeper into this ocean of thought, we find a crisis brewing at the heart of mathematical formalism. This crisis, sparked by Gödel's theorem, challenged the very notion that mathematics could be entirely grounded in clear-cut logical and axiomatic foundations. The formalist approach, which sought to build a fortress of mathematical knowledge upon the bedrock of axioms and logical inference, was profoundly shaken. Gödel's theorem suggested that no matter how solid our logical foundations might be, there will always be truths that elude our formal systems. This notion, akin to finding a room in your house that you can never enter, sent tremors through the world of mathematics. It was as if the very idea of a complete and consistent system was revealed to be a mirage. But the impact of Gödel's theorem didn't stop there. It also played a crucial role in discussions about self-awareness and reflexivity in logical systems. Gödel employed techniques of self-reference in his proof, essentially making the system talk about its own consistency. This twist, reminiscent of a mirror reflecting upon itself, brought a new dimension to the discourse on logical reflexivity. Imagine a system capable of contemplating its own consistency, much like a sentient being reflecting on its own existence. Such a concept stirs the imagination and raises fascinating questions about the nature of self-awareness. Can a logical system be reflexive? Can it know itself in the same way we know ourselves? These are questions that continue to intrigue thinkers across disciplines, from mathematicians to philosophers, and even cognitive scientists. Gödel's theorem, therefore, not only questions the completeness of mathematical systems, but also the very nature of self-awareness and reflexivity. It's a theorem that truly pushes the boundaries of what we thought was possible in mathematics and logic, urging us to rethink our understanding of knowledge and the universe itself. Gödel's incompleteness theorem continues to resonate, challenging our understanding of mathematical truth. As we delve into the enduring implications of Gödel's theorem, we find ourselves faced with the very limits of mathematical knowledge and the intrinsic nature of mathematical truth. This theorem, a product of the brilliant mind of Gödel, has served not only as a cornerstone for mathematical logic, but also as a catalyst for philosophical thought. For decades, mathematicians and philosophers alike have grappled with the profound implications of Gödel's theorem. It has been a humbling reminder that even in a field as precise and logical as mathematics, there are truths that lie beyond the reach of our comprehension. These truths, forever elusive, remind us of the inherent limitations of formal systems, no matter how meticulously they are constructed. The theorem's influence has permeated beyond the realm of mathematics, sparking discussions on the nature of self-awareness and reflexivity. By demonstrating that a system can express statements about its own consistency, Gödel has opened a door to a world where logical systems are not merely tools for computation, but entities capable of self-reference. This has led to intriguing questions about consciousness and the nature of self-awareness. Moreover, Gödel's theorem has challenged the very foundations of mathematical formalism, shaking the belief in a complete and consistent system. This has ushered in a new era of mathematical philosophy, where the quest for a complete understanding of mathematical truth is not a destination, but a journey a journey filled with enigmatic truths, paradoxes, and challenges that keep mathematicians on their toes. In the grand scheme of things, Gödel's theorem has not only reshaped our understanding of mathematical logic, but also redefined our perception of knowledge itself. It has taught us to question, to challenge, and to embrace the unknowable. In the world of mathematical logic, Gödel's theorem serves as a humbling reminder of the limits of our understanding, a testament to the enigmatic nature of truth itself.